Alright, picture this. You're aboard a sleek spaceship, cruising through the galaxy. You punch in the destination, Alpha Centauri, only 4.37 light-years away. At the speed of light, it would take just over 4 years to get there. But you're hoping to get there faster. Way faster. You kick the engines into high gear and nothing happens. Why? Because no matter how advanced your technology, how powerful your engines, or how desperately you want to break the cosmic speed limit, physics says nope. So that brings us to today's question. Why can't we travel faster than light? Is it just a technical problem we haven't solved yet? Or is it a fundamental law of the universe that makes faster than light, FTL, travel forever impossible? Let's break it down, from Einstein to wormholes to the dreams of science fiction. The speed limit of the universe. Let's start with a fact that's as wild as it is frustrating. The speed of light is the universal speed limit. Roughly 299,792 kilometers per second, or about 186,000 miles per second. That's fast. Really fast. Like go around the Earth 7.5 times in 1 second fast. But according to Einstein's theory of special relativity, nothing with mass can reach, or exceed, that speed. Here's why. The faster you go, the more energy it takes to keep accelerating. And as you approach the speed of light, your mass, from the perspective of an outside observer, increases toward infinity. Which means, it would take infinite energy to actually reach light speed. And we don't have infinite anything. What does relativity even mean? Einstein's big idea in 1905 wasn't just about speed, it was about how time and space behave at high velocities. Special relativity showed us that space and time aren't fixed, they're flexible. The faster you move, the more time slows down for you. This is called time dilation. At near light speeds, time would practically stop for the traveler, while years could pass for someone back on Earth. Sounds cool, right? But here's the kicker. No matter how fast you're going, light always moves away from you at the same speed. It doesn't matter if you're standing still or going 99.9999% the speed of light. Light still zips away from you at the same rate. That's not just a weird quirk, it's a rule baked into the fabric of the universe. And that rule is what keeps faster than light travel permanently off the table. Or so we think. The energy wall. Here's a thought experiment. Imagine you're in a spaceship with a futuristic engine, something way beyond what we have today. You crank the throttle and start speeding up. The faster you go, the heavier your ship gets. Not because you're gaining mass in the traditional sense, but because of relativistic mass increase. Your kinetic energy adds to your effective mass. By the time you're going, say, 90% the speed of light, every extra 1% of speed takes exponentially more fuel. And at 99.9999% the speed of light, your engine would need energy on the scale of entire galaxies just to budge you forward a little more. So in practical terms, it's not just difficult, it's impossible. But what about light itself? Light doesn't have mass. That's how it can move at light speed. Photons, particles of light, are massless, and that's the cheat code. They don't have to worry about all this relativistic buildup. But anything with even a speck of mass? Trapped below that limit. Forever. Warp drives and wormholes, sci-fi workarounds. Of course, this hasn't stopped anyone from dreaming. Enter warp drives, wormholes, and hyperspace. Let's take a quick tour. Warp drives. Made famous by Star Trek, the idea is to bend space itself. Instead of moving through space faster than light, you compress space in front of you and expand it behind. You're not breaking the light speed limit, you're sidestepping it. The most famous theoretical model? The Alcubierre drive. It's mathematically possible in general relativity, but there's a catch. It requires negative energy, a form of exotic matter we've never observed in usable amounts. And even if we could harness it, the energy requirements are astronomical. Wormholes. Another Einstein idea, expanded by later physicists. Wormholes are shortcuts through space-time, connecting distant points. In theory, you enter one side and exit somewhere else instantly, without traveling faster than light locally. But again, massive issues. They'd collapse instantly, likely be incredibly unstable, and once again, require exotic matter to keep open. Still, some physicists haven't ruled them out entirely. So are they real? Maybe. Are they practical? Not even close. Is FTL always off the table? Well, let's ask a different question. Is the speed of light truly an unbreakable barrier, or just a wall we don't know how to climb yet? The truth is, physics as we understand it doesn't allow FTL travel. But that's just it as we understand it. Every now and then, fringe theories and quantum mechanics offer little glimpses of hope. Some particles seem to communicate instantaneously, like entangled particles in quantum experiments. But they don't transmit usable information faster than light, which means they can't help us build a spaceship. So far, no experiment has ever shown a clear way to send matter or information faster than light without violating causality, the idea that cause comes before effect. And if you mess with causality, well, you get time travel, paradoxes, and a universe that stops making sense. So yeah, the speed of light is more than just fast. It's the boundary between logic and chaos. Even near-light speeds are wild. Let's slow it down a bit. What if we only travel at 90% the speed of light? At that speed, a journey to Alpha Centauri would take about 4.8 years from Earth's perspective. But for you on the ship, it might feel like a few months due to time dilation. You'd age slower than everyone back home. Even without FTL, near-light speed travel opens the door to some serious interstellar weirdness. But building a craft that can withstand the energy, heat, radiation, and navigation challenges of those speeds? Still far beyond what we can do. So what's the future? For now, humanity is stuck crawling through space. We've sent probes to the outer solar system. We've landed rovers on Mars. We've built telescopes that can peer across billions of light years. But our ships? They move like snails compared to the cosmic scale. Even the fastest spacecraft ever built, NASA's Parker Solar Probe, only hits about 0.06% the speed of light at its peak. To us, that's fast. To space? It's basically standing still. Final thoughts. So, why can't we travel faster than light? Because the universe is built that way. Because light speed isn't just a limit, it's the scaffolding of space-time itself. To break it would be to rewrite the laws of physics as we know them. That doesn't mean we should stop dreaming. The greatest breakthroughs often come from asking what if, and pushing the boundaries of possibility. But for now, if we want to explore the stars, we'll need to either be very patient, find creative loopholes in the rules, or discover a new kind of physics entirely. Until then, light speed is as fast as it gets. If this cosmic speed limit blew your mind, hit like, subscribe, and share this with your favorite sci-fi lover. And drop this in the comments. If faster-than-light travel suddenly became possible, where would you go first? Until next time, stay curious, stay grounded, and remember, the universe doesn't care how fast we want to go. It just plays by its rules. And it's up to us to find the hacks.